Hello friends, welcome to physics class. Today we discuss EMF, terminal potential and internal resistance of a cell. You know that a electrolytic cell is a device which can maintain a steady flow of current through an electrical circuit. Every electrochemical cell or electrolytic cell consists of two terminal. One is positive terminal and other is negative terminal. Usually these terminals are immersed in a fluid known as electrolyte. So when they are immersed in an electrolyte, they can exchange the charges with the electrolyte. Due to some unknown force, due to some chemical reaction, some force is originating. It is not electrostatic force, and because of that force, the charges are attracted towards the positive and negative terminal. That is, some positive charges are moving towards this P and negative charges are moving towards the N, and they accumulated at a P and N. This terminal we calling positive terminal and this we calling as negative terminal. And this process will continue until the electrostatic repulsive force balance this natural unknown force. So because of this charge accumulation, there is a potential difference between these two terminals. And that potential difference is known as the EMF of the cell. Now the cell is not working, no current is drawn from the cell, no external circuit is connected to the cell, but still there is a potential difference between this positive and negative electrode. That potential difference is known as the EMF of the cell. And the EMF, actually the full form is electromotive force. Electromotive force. Even it is named as a force, it is only a potential difference, it is not a force. The naming has some historical reasons, because when the name is given, the phenomena behind this potential or EMF is not known. That's why the name is so as electromotive force. Actually, it is only a potential difference. It is measured in volt. And it is defined as the electromotive force of a cell is the potential difference across its terminals when no electric current is flow through it or it is in an open circuit, and it is denoted as E and it is measured in volt. Now because of this charge accumulation, there is some potential difference, but there is no external circuit to this cell. No current is drawn from the cell. Now the potential difference we calling as EMF of the cell, electromotive force of the cell. This is the maximum possible potential difference between these two terminals. Now suppose we are connecting some external circuit to this battery, that is we are connecting a resistance, an external resistance R is connected to this battery. An external resistance R is connected to the battery. Now current is drawn from the battery or current is drawn from the cell. Some current is flowing through this circuit. In the external resistance, the current is flowing from P to N. In the external resistance, current flows from P to N. And inside the cell, N to P, there is a current or charges flows from the negative terminal to the positive terminal, from N to P inside the cell. When current is flowing through this electrolyte, it offers some resistance to the flow of current. That is, every electrolyte offering a very small resistance to the flow of current. Actually, that resistance is inside the cell itself, and that resistance we calling as internal resistance of the cell. That is, when some external resistance or external circuit is connected to a cell, the current starts flowing through the cell, and when the current is flowing through this electrolyte, it offers some resistance, a very small resistance, and that resistance offered by the cell or electrolyte of the cell is known as internal resistance of the cell. And internal resistance, the resistance offered by the electrolyte of a cell to the flow of current between its electrode is the internal resistance, and it is denoted as R. The internal resistance of a cell depends on the various factor like as the surface area of the electrode. We told every electrolytic cell have two electrodes. One is positive and the other one is negative. Actually, it depends on the internal resistance depends on the surface area of the electrode. The second factor is the distance between these two electrodes. The electrodes are separated by some distance. The internal resistance of the cell also depends on the distance between the two electrodes. And the internal resistance also depends on the following factor. One is the nature of the electrolyte. We can take different types of electrolyte. So it depends on the nature of the electrolyte. When the electrolyte change, the internal resistance also change. Then it depends on the temperature. When the temperature change, the internal resistance also change. The concentration of the electrolyte, the concentration, when the concentration change, the internal resistance also change. So these are the factors which affecting the internal resistance of a electrolyte or internal resistance of a cell. And however, all cells having some small internal resistance. Now, because of this internal resistance, when current is flowing through the external circuit and through the cell, some potential is dropped because of this internal resistance. Because of this internal resistance, some potential will drop across this internal resistance. So, the EMF is reduces because of this internal resistance. Now, let us see what is the terminal potential difference. What is the terminal potential difference of a cell? We told that the current is flowing through the external circuit and the internal circuit. So the potential drop across the terminals of a cell when current is being drawn from it is called terminal potential difference. The terminal potential difference, the potential drop across the terminals of a cell when current is being drawn from it is called terminal potential difference, and it is denoted as V. You know that I current is drawn from this cell, so the total EMF is dropped across resistance, that's our external resistance, and some is dropped across the internal resistance. If V is the potential drop across the external resistance, V is the potential drop across the external resistance, and V dash is the potential drop across the internal resistance. That is, the total EMF of the cell is divided into V and V dash. V is the potential drop across the external resistance, and V dash is the potential drop across the internal resistance. Now we can write as E is equal to, by Ohm's law, potential difference across the external resistance can be write as the I into R, where I is the current passing through the external resistance. The same current is flowing through the internal resistance also. If R is the internal resistance of the cell, we can write I into R is the potential difference across the internal resistance. So I into R plus I into R, small letter R, will be equal to the total EMF. Now we can rewrite like this. The EMF E is equal to, we taking I outside of this bracket, I into R plus R. Or the current drawn from the cell can be write as I is equal to E by R plus R. If the internal resistance of the cell is negligible, we can write simply I is equal to E by R, where E is the EMF of the cell and R is the external resistance that we are connected to the circuit. Now, in order to denote this internal resistance of a cell, when you are drawing a circuit diagram, now we are drawing this electrolytic cell like this way only. This is the symbol, circuit symbol for a cell. This is the positive terminal and negative terminal. Along with this cell, we have a small resistance. Inside the cell itself, we have a very small resistance. That is our internal resistance. There are two methods to represent this internal resistance. One of the way is we can draw here, it having some a small resistance. To show the cell having a small resistance, we can draw here. Otherwise, we used to draw along with this cell a small resistance. That is the internal resistance of the cell. That is marked as R. And this is the external resistance. A current I is drawn from the cell. So total current I is equal to E by R plus R. I is equal to E by R plus R. Now the potential across this external resistance, the potential difference across this external resistance, or otherwise we can call it as terminal potential difference. When the cell is working, the potential difference between this terminal is only the potential difference across this resistor. So the terminal potential of the cell can also write as V is equal to I into R, where R is the external resistance to the circuit. V is equal to I into R. Now V is equal to, substitute for I. What is I? I is equal to E by R plus R. E by R plus R into external resistance R. Or otherwise, one more method, we can write V is equal to, from this equation, V is equal to E minus V dash. The terminal potential of the cell, V is equal to EMF minus V dash. What is V dash? V dash is the potential drop across the internal resistance. E minus V dash. V dash can be write as, what is V dash? V dash is equal to I into R. So V is equal to terminal potential difference. V is equal to E minus I into R. V is equal to E minus I into R. Now an expression for the internal resistance of a cell, we have R from this equation. We are rearranging this equation and writing the expression for the internal resistance of a cell. R is equal to E minus V by I. Internal resistance R is equal to E minus V by I. Or if you are writing what is the current in the external circuit, now current I is equal to V by R. Current I is equal to V by R. Rearranging, we get an expression for the internal resistance. R is equal to E minus V by V into capital R. That's the expression for the internal resistance of a cell. Every cell having an internal resistance, and it depends on the following factor: surface area of the electrode, distance between the two electrodes, and nature, temperature, and concentration of the electrolyte. Now let us see some characteristics curve for a cell. First, we are drawing a graph between the EMF and external resistance. You know that EMF is the potential difference between the terminals when no external resistance is connected. So we can say external resistance and EMF of a cell are independent. So we're getting a straight line parallel to the x-axis or resistance axis. E versus R graph is a straight line parallel to the x-axis. Now a graph between the terminal potential and the external resistance. We know that the terminal potential can write as the current drawn from the cell into external resistance. V is equal to I into R. So we are plotting a graph between the V and R by taking the R external resistance on x-axis and terminal potential on y-axis. First, put R is equal to 0. In this equation, when R is equal to 0, we can write when R is equal to 0, V is equal to what? 0. So here, when external resistance is equal to 0, terminal potential difference is equal to 0. Now, we are rewriting this equation as V is equal to, instead of I, we are writing E by R plus R. E by R plus R into R. And taking one R outside and cancel here. And V is equal to E by 1 plus R by R. E by 1 plus R by R. Now substitute when R is equal to R, that is external resistance and internal resistance are same. When in this equation, when putting R is equal to R, R and R getting cancelled. V is equal to E by 2. V is equal to E by 2. That is, when external resistance is equal to internal resistance, the terminal potential difference is the half of EMF. That's the point is here. When R is equal to R, V is equal to E by 2. When R is equal to infinite, we can write as substitute R is equal to infinite here, V is equal to E. V is equal to E. That is, when R is equal to infinite, V is equal to E. So this characteristic curve is like this. When external resistance increases, the terminal potential is increases. And terminal potential become EMF when external resistance is equal to infinite. That is in open circuit. Now the third graph is potential with the current. That is terminal potential versus current graph. So we are taking the current on x-axis and terminal potential on y-axis. When current is equal to 0, we know that no current is drawn from the cell. The terminal potential difference and EMF are same. That is, when I is equal to 0, V is equal to what? V is equal to E at this point. When current is increases, this is the equation actually, the terminal potential difference V is equal to E minus I into R. When I increases, terminal potential gradually decreases. So when I increases, V decreases, and when the current is maximum, what comes? V comes to 0. The terminal potential difference comes to 0. That is, we can write as for a maximum current, V is equal to 0. This is the V equal to 0, and current become I maximum. The current become I maximum. So we can rewrite like this way, that V equal to 0. 0 is equal to E minus I maximum into R. I maximum into R. So we can write as E is equal to I maximum into R. The EMF E is equal to I maximum into R. Or the internal resistance of the cell R is equal to E by I maximum. EMF by I maximum. Actually, this is the slope of VI graph, the negative of the slope of VI graph. So when you are getting a VI graph for a cell, VI characteristics of a cell, we can find the internal resistance of a cell by finding the negative of slope of VI graph. That's all today. Thank you.